Hi everyone, myself Dr. P. Ashok Babu, working as Professor and Head EC Department. So in this video, I am going to discuss about the wave propagation in good conductors and the important concept of depth of penetration. So in previous video, we have discussed about the wave propagation in a good dielectric. Now we are going to discuss about the wave propagation in a good conductor. So for good conductor, here we need to assume that the ratio sigma by omega epsilon is very greater than 1. When the ratio sigma by omega epsilon is very greater than 1, then we can assume the material as a good conductor. So that the expression for gamma may be written as here the gamma is a propagation constant. Gamma is equal to, we have the expression root of j omega mu into sigma plus j omega epsilon. So it is the expression for propagation constant. So where gamma is equal to alpha plus j beta, where alpha is the attenuation constant, beta is the phase shift constant. Okay, so here let us assume the propagation constant gamma. So in that propagation constant, you take a common of sigma. Here, if you take a common of sigma, the equation becomes root of j omega mu sigma into 1 plus j into omega epsilon by sigma. So here gamma is approximately equal to here because we assume the good conductor. For good conductor, sigma by omega epsilon is very greater than 1. If sigma by omega epsilon is very greater than 1, omega epsilon by sigma is very less than 1. Omega epsilon by sigma is very less than 1. Then we can ignore this particular part. So here if we ignore the omega epsilon by sigma, then we have the equation gamma is approximately equal to root of j omega mu sigma. So here because of j can be expressed as an angle. So therefore it is root of omega mu sigma into angle 45 degrees. Angle 45 degrees. But we know that the alpha, the phase shift constant, the attenuation constant alpha is equal to omega into root of mu epsilon by 2 into root of 1 plus sigma square by omega square epsilon square minus 1, which is equal to, so here sigma by omega for good conductor, sigma by omega epsilon is very greater than 1. Therefore, so here we can ignore the 1 here, and if we take out of the root, it is root of omega into root of mu epsilon by 2 into sigma by omega epsilon minus 1. Here also compared to 1, sigma by omega epsilon is very greater than 1. Therefore, the expression for alpha becomes alpha is equal to omega into root of mu epsilon by 2 into sigma by omega epsilon. So here omega epsilon can be cancel each other. Therefore, alpha is equal to, we have omega into root of mu sigma by 2 omega. Mu sigma by 2 omega. Again, if we simplify that equation, alpha is equal to root of omega mu sigma by 2. Here, if we move the omega into root, therefore the equation becomes alpha is equal to, it is root of omega square mu sigma by 2 omega. Omega cancel each other. Therefore, alpha is equal to root of omega mu sigma by 2. The expression becomes alpha is equal to root of omega mu sigma by 2. And here we can write the expression as alpha is equal to beta, which is approximately equal to root of omega mu sigma by 2. Omega mu sigma by 2 for good conductor material. So here we can define the velocity also. Velocity, and we can define the intrinsic impedance for the good conductor. Same as the good dielectric, we need to define the phase velocity and intrinsic impedance. Here we can define the velocity V is equal to omega by beta, where beta is known as root of omega mu sigma by 2. Therefore, omega by root of omega mu sigma by 2. If we simplify the equation, so here it is. It becomes, if it is in root, we have, it is omega square 2 by omega mu sigma under root omega cancel each other. Therefore, it becomes root of 2 omega by mu sigma. 2 omega by mu sigma. The intrinsic impedance of the conductor is, already we know the intrinsic impedance. Eta is equal to j omega mu by 1 plus sigma plus j omega epsilon. Actually, we have eta is equal to root of j omega mu by sigma plus j omega epsilon is the formula for intrinsic impedance. So here if we take a common of j omega epsilon from the equation, so j omega mu by j omega epsilon into 1 plus sigma by j omega epsilon, which is equal to root of mu by epsilon. Here we can take we can cancel the j omega. If we cancel j omega down, then here root of mu by epsilon into 1 by 1 plus sigma by j omega epsilon. So it is, we can further simplify the equation as it is root of mu by epsilon into, so here 1 by 1 plus sigma by j omega epsilon. Here sigma by j omega epsilon, for good conductor, sigma by j omega epsilon is very greater than 1. Therefore here we can ignore the 1 and the equation becomes root of mu by epsilon into 1 by sigma by j omega epsilon. It is j omega, we can cancel the epsilon and epsilon. Therefore the equation becomes root of j omega mu by sigma. And here we can express the j as angle 45 degrees. Therefore the intrinsic impedance eta is equal to root of omega mu by sigma into angle 45 degrees. So in this way we can find out the expression for phase shift constant, attenuation constant alpha and phase shift constant beta, then the velocity, phase velocity v and intrinsic impedance for a good conductor material. So it is seen that in good conductors where sigma is very large, both alpha and beta are also large values. So this means that the wave is attenuated greatly as it progresses through a conductor and the phase shift per unit length is also great. So here the velocity of the wave being inversely proportional to beta, the velocity of the wave, because we know the velocity v is equal to omega by beta. We know the velocity v is equal to omega by beta. Therefore omega v, the phase velocity v is directly proportional to the phase shift constant beta, inversely proportional to phase shift constant beta, is very small in good conductors and is of same order of the magnitude as that of the sound wave in air also. So here the characteristic impedance is also very small and has a reactive component. The angle of this impedance is always 45 degrees for good conductors, whereas for good dielectric there is no angle and angle will be 0 there. Whereas for good dielectrics the angle is around 45 degrees always. So this is about the wave propagation in good conductors. Now we will discuss one of the important topic, depth of penetration. So here first we will define the what is the depth of penetration. So the depth of penetration is denoted as delta, and the depth of penetration delta is defined as the depth in which the wave has been attenuated to 1 by E or approximately 37% of its initial value or 37% of its original value. Since the amplitude decreases by a factor of e power minus alpha x, it is apparent that the distance x which makes alpha x is equal to 1. Alpha x equal to 1. So here the amplitude is only 1 by e times its initial value at x equal to 0. So therefore by definition of its distance, the distance can be, here we can assume the distance as skip distance. Therefore in place of x we can assume skip distance delta. Therefore alpha into delta is equal to 1, or the skip distance delta is equal to, simply we can write 1 by alpha. Already we know the attenuation constant alpha value. Therefore delta is equal to 1 by alpha, which is equal to 1 by, in place of attenuation constant, here I am writing the value of attenuation constant. Therefore alpha is equal to omega into root of mu epsilon by 2 into root of 1 plus sigma square by omega square epsilon square minus 1. Directly we can write the value, shortcut value is the skip distance for good conductor. For good conductor, the depth of penetration is, the previous one is, it is a general formula for depth of penetration. The depth of penetration for good conductors is delta is equal to 1 by alpha, which is approximately equal to root of 2 by omega mu sigma. Root of 2 by omega mu sigma. So here as an example, we'll see some good conductor and good dielectric. So an example of order of magnitude of delta in metals. The depth of penetration of a 1 megahertz wave into copper, which has a conductivity sigma is equal to 5.8 into 10 power 7 is equal to the is equal to that of free space is, here you can calculate the depth of penetration by substituting the values. Therefore, depth of penetration delta is equal to, so it is 2 into 10 power 7 by, it is 2 pi into 10 power 6 into 4 pi new value, 4 pi into 10 power minus 7 actually, 4 into 5.8 into 10 power 7. So here if you find out the value, the depth of penetration is 0.0667 millimeters. So it means at 1 megahertz, the depth of penetration is 0.0667 millimeters. Again, if you assume 100 megahertz, the depth of penetration is 0.00667 millimeters. The depth of, as frequency increases, the penetration value decreases. So whereas at 60 hertz, it is 8.67 millimeters. So for comparison, at 1 megahertz, the depth of penetration is 25 centimeters into seawater or salt water. And whereas for fresh water, it is 7.1 meters into a fresh water. So here if you compare the fresh water and seawater, in seawater, the depth of penetration is 25 centimeters in seawater. And the depth of penetration is 7.1 meters into a fresh water at 1 megahertz. So from this we can observe that in seawater the depth of penetration is very low, and whereas in fresh water the depth of penetration is very high. And at if we increase the frequency range, the depth of penetration will decreases. So this is about the depth of penetration, definition and depth of penetration. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.